Hello everyone and welcome to another sound design lecture where today we will be talking about filters, specifically digital audio filters and how filtering is done within the Web Audio API. So first off, linear, time-invariant digital filters are at the heart of many audio effects. Graphic equalizers, parametric equalizers, anti-aliasing filters all fit this framework, and variations on such filters are the basis for flangers and phasers and so much more. And this type of filter is not restricted to audio. It has wide application throughout signal processing. So we're going to just focus on some of the essentials, which means we leave out a lot of theory but give enough to understand their use. And we're not going to formally define a lot of terms but give you just enough. So we're not going to focus on the time invariant aspect, but it does mean that time is not an explicit parameter of the filter. And we're not going to focus on linearity. But the basic idea of all of these linear time invariant digital filters is that the current output sample, the output of the filter, is just a function of the current inputs, the past inputs, and the past outputs, all summed together with different weights applied. So it can be written as the equation below right here, where I see a tiny little typo, which I will fix. The equation right here, which is if you take the current output and the previous output and the one before, you have coefficients for all of them, that equals some weights applied to current and previous outputs, which means you can put everything but the y of n term on one side and you're left with current output y of n is just this weighted sum of the current input, the past inputs, and past outputs. So a few examples of different filters that have this form. If we just delay a signal by some number of samples, capital D for the delay, then that output y of n is equal to this delayed version of the input. So we're really only keeping one term over here, one past input value. If we just average a value and the previous value, then that's also dependent only on past outputs. And here we have the or current and past output. We have two values averaged together from the output forming the input. And then there's exponential smoothing, which is a first order IIR filter. We'll talk about IIR in a minute. But that sort of filter looks like this, where the current output is a weight of the current input value and the most recent output value. So if this coefficient C is close to 1, then the output is going to be very similar to the input. If the coefficient C is close to 0, then the output changes very slowly with inputs. It tends to keep the same value of output and will respond to a change in the input only very slowly over time. So those are three examples of simple digital filters. Now, a few more points to say about the filters. The filter can be completely described by the coefficients. So when working with the filter, you often don't need to write down this difference equation. You may not write it down in other forms or a block diagram. You just need to give a set of coefficients. There's one caveat there. You should know, in order to describe how the filter responds to a signal, you should know what the initial value of that filter is going to be. Generally, we assume it's going to be 0, but if we have a filter like this one on at the very bottom here, y of n equals coefficient c times x of n plus 1 minus c y of n minus 1, well, what if we're at the very first input x of 0? What's y of 0 minus 1? We don't have any previous outputs, but usually one assumes that that value is just 0. So filters are described by the set of coefficients, and these filters affect magnitude and phase of the frequencies in a signal. They don't affect things in very bizarre ways. If there's if some frequency is not present in the input signal, then this linear time invariant operation won't introduce that frequency. It can simply change the magnitude of it, multiply it by 2 or divide it by 2, something like that. So let's give an example here. Suppose we have an input, it's just a sine wave. I'm not fussed about what particular frequency it is. There's a initial phase of 0 for this wave, and I apply that averaging filter that we saw on the previous slide. So 1/2 the current input and the previous input. The output, after applying this filter, you just plug in the value of x of n, which is the sine of x, or sorry, sine of n, for where n is the sample number. The output then is y of n equals sine of n plus sine of n minus 1 over 2. I just took these two coefficients, 0.5 and 0.5, and made it over 2. A little bit of trigonometry says that this value right here can be rewritten in terms of cosine of this term n minus this term n minus 1, and sine of this term n plus this term n minus 1, where factors of 2's need to be included, and there's a 2 in front, but that cancels with the dividing by 2. So it looks like this. This is what the output is for that given input. So we still have sine of n, but now there's a phase change, and rather than a magnitude of 1, there's now a new magnitude, cosine of 1/2. So what did this filter do? It changed the magnitude, and it changed the phase, but you input one particular frequency, sine of n, you still get a sinusoid at that same frequency. So that's what these filters do. For any given frequency input coming in, it will change that magnitude by some amount, change that phase by some amount. So that's the idea of the filters, but there's many different types of filters. Essentially, you can have almost any function between a frequency of 0 and the maximum frequency that can be captured when you're sampling at a particular frequency. You can have any function describing how the magnitude changes or how the phase changes. But there's a few that are particularly useful. One is the low-pass filter. It basically tries to remove all the high-frequency content and keep only the content below some cutoff frequency called f sub c here. And the highest frequency we can deal with is 1/2 the sampling frequency. So if the sampling frequency is fs, then we plotted it from 0 to fs over 2. Another important ideal filter is the high-pass filter, which tries to remove all of the low-frequency content up to that cutoff frequency and keep the higher frequencies. Similar to those two, we might have a filter that tries to remove all content except for content over a particular range, where it tries to leave that unaffected. And so that would be a bandpass filter, where now we have two important parameters. Choice of where this cutoff frequency is, only here it's actually a center frequency for the center of a particular region or frequency band that can be defined by its range, known as bandwidth, B for the bandwidth. And similar to the bandpass, we have a band stop filter, often given other names, but the basic idea of this filter is that it keeps all of the frequency content except for the content over some frequency band. Same two parameters here, the center frequency and the bandwidth. A few more ideal filters. I call them ideal filters because in most filter implementations you won't have anything like this very sharp transition. It will be much smoother as it goes from some level there down to some level. Anyway, you have a low shelving filter. The idea there is that it leaves the high frequencies above some cutoff unchanged, but it can boost, increase the low frequencies, or it can attenuate them. So it need not be, this value G for how much gain, need not be greater than 1. It could be less than 1. High shelving filter is the same idea, only now the boost or cut is happening just at the high frequencies. The peaking filter is the same idea as well, only now this boost or cut is happening just over a frequency band. And symmetric to boosting, you could also cut it. Now here the terminology is awkward because some people will refer to this cut as a notch. Some will treat just the boost or cut as a peaking filter. That's how it's done in the Web Audio API. But if you try to treat a notch differently, then that notch is really like the band stop filter. But anyway, let's leave that to the side. We'll show how the Web Audio API does it in just a few minutes. Okay, so those are some standard filter types that one sees over and over again, especially in audio. And how do they look in the real world? The transitions are a lot smoother. Here we're showing it on a different scale with decibels or logarithmic scale on the y-axis, but the same idea. Low pass, keeping low frequencies, and then removing the higher frequencies. High pass is the opposite type of behavior. Band pass is nowhere near as ideal as shown. Here it looks more like a triangle shape, but it's trying to keep some of the frequencies in this range. Then we have the peaking or notch filter. Again, the Web Audio API will call this just peaking filters and treat the notch filter more like the band stop filter. And we have the shelving filters. Here I've just shown a low shelving filter, but you know already how it might look for the high shelving filter, and an all pass filter. Now the all pass filter here is leaving the signal completely unchanged. It's not really doing anything to the magnitude of the signal. So what is it changing? If it's not changing magnitude, because we're plotting the magnitude of the signal that comes out for different frequencies that come in, well, it only changes the phase. It means that the signal is delayed, and it can be delayed significantly different amounts in different ways for different frequencies of inputs, but that's the effect. Any frequency in the input can be delayed in different amounts by the all-pass filter without changing the magnitude of the signal. Okay, when we talked about a few filter parameters that were shown, we showed the bandwidth as well as the center frequency and a gain. Well, we often talk about Q, or quality factor, instead. And one of the reasons why people work with Q is it's quite awkward if you've got a very low frequency filter, say an audio filter of around 50 Hertz. You would never have a bandwidth of 200 Hertz. But if you had a filter of, say, 12 kilohertz, then a 200 Hertz bandwidth is actually quite narrow. So really what someone is interested in is how narrow or how wide is the bandwidth in comparison to where the center frequency is. So we use Q, which is center frequency over bandwidth. Essentially, when Q is very low, whatever is the transition, whatever is the sharp, peaky behavior we're trying to produce, when Q is very low, it's very broad or slow transition. When Q is very high, then you get a sharp peak in the behavior if you're trying to establish something like a resonance, or you're getting a very steep transition. So it can look more like those idealized filters that we showed previously. Here's an example of what's called a second order low pass resonant filter. The idea of these filters, which are used heavily in the web audio API, but are by no means the standard filters to use in audio for low pass. But the idea with these filters is that it keeps the low frequencies relatively unchanged. It filters out the high frequencies, but it produces a sort of a peak right when it transitions to filtering. So it's sort of like you go the wrong way in order to then go really fast. Think of a car that pulls back a second before going fast. Well, that's what's happening with this peaky behavior here. And when the Q is set high, as is the case in the red curve, it becomes a much stronger peak. When the Q is set low, you hardly see the peak at all. It's much more similar to actually a first order low pass filter, not a resonant filter. And it just sort of slowly transitions to the low pass behavior, or to removing the high frequencies. Okay, so let me just make sure I have, yes, I did miss a slide, so bear with me. Okay, so how do we do the filtering in the web audio API? Well, the filter is just an audio node like the other audio nodes that you've seen. It's not a source node. It requires some source as the input signal, and it filters that signal to produce the output. It does the same filtering on every channel of the signal coming in, if it's a stereo signal or a surround signal. And there's two different nodes for filtering. They work in quite different ways, but they're still both doing digital linear time invariant filters. We have the Biquad filter node, where the filters are always what's known as second order. So in terms of these A and B coefficients, it always only goes up to 2, A0, A1, A2, B0, B1, B2. And the parameters, when using a Biquad filter node, they specify the type of filter, like is it all pass, is it a peaking filter, and attributes. What are the gain, center frequency, and bandwidth? The IIR filter works differently. So first, what do we mean by IIR? IIR stands for an infinite impulse response. It just means that these A1, A2, and potentially higher coefficients, A3, A4, are not all 0. That means the filter has feedback. It depends on past outputs. So if the input is a single pulse, then it will generate an output based on that pulse, and the next output will depend on the previous output, and the next output depends on that previous output, and so on. So it responds forever. That's what we mean by an infinite impulse response. That's opposed to a finite impulse response filter, where those A values are all 0, so the current output depends only on previous inputs, which means that once you've finished going through those previous inputs, there is no more output. The output will be 0 if there's nothing in the input. So the response to an impulse is finite. It stops. Okay, so that's the idea of IIR. The IIR filter node doesn't have to be second order. It is arbitrary order up to a limit, which I think might actually be a number like 32 or something like that. but for a lot of applications, that would be a quite high order IIR filter. So you can have quite complicated filters that do really crazy things with that magnitude response. And when working with the IIR filter, you don't specify filter attributes like gain and bandwidth. They can mean very different things when you have these very complicated high order filters. So one specifies directly the filter coefficients. One has two arrays, one of the A values and one of the B values. But this filter, as it's implemented in the Web Audio API, is very difficult to work with. Once a node has been created, you can't change its coefficients. So it's no longer interactive, no longer something you can adapt. You can't do automation curves to vary a coefficient over time, or have the coefficients be linked to or have an oscillator node connected to the coefficients. Now, you may not want to do all of those things, but you would still like to at least be able to change its coefficients sometimes, some ways. There's only a handful of narrow applications where you wouldn't want to do that. Like if you want to make sure you always apply some filter, some fixed frequency filter to the signal, because you know you're going to be listening to it where you want to remove all the high frequency content. The high frequency content might be causing aliasing on your device or something like that. So that might be an application where you would want the IIR filter. But generally, it doesn't fit the whole idea of this data flow interactive programming of the Web Audio API. So we're not really going to deal with the IIR filter node. We'll stick to the Biquad filter node. So what do we do, by the way, if you want to use a filter that is not one of the ones in the Biquad filter node? You can use audio worklets. And in a different lecture, we've talked about audio worklets, and we've shown constructing a fairly simple filter with an audio worklet. It's not that complicated. So it would be possible to build an IIR filter with additional functionality. The problem, though, when changing IIR filter coefficients is it's very easy, especially with high-order designs, for the filter to go unstable. The wrong choice of coefficients means that the output for a given input will be higher magnitude, and then you feed that higher magnitude output back, and the output after that will be even higher, and it goes off to infinity. Very easy to do that. So if you are going to design higher order filters, you need to be very careful with their design. But let's stick to the Biquad filter. So this table right here is showing all the types of Biquad filters that are built into the Web Audio API, and a little bit describing anything interesting about how they are implemented or what it means, and which parameters are used and what those parameters mean. So first off, we have low pass and high pass, band pass filters, low shelf and high shelf. Those mean the same in every situation. But here, the peaking filter, they refer to the same type of filter whether it has a boost or a cut. Their notch filter is what others refer to as a band stop filter. So it's very different from, say, taking the peaking filter and trying to apply as much cut as possible. The notch filter fully aims for it to remove the signal completely. Okay, so, and then of course there's the all pass filter. So the frequency parameter in each of them is either referring to some cutoff frequency where it transitions from keeping frequencies to removing frequencies, or from boosting or cutting frequencies to leaving them unchanged, or it may refer to the center frequency of a frequency band that you want to boost, or you want to cut, or you want to remove, or you want to keep while everything else is removed. So that's center or cutoff frequency. And the all-pass filter also has a transition in most designs in the phase behavior. It might transition from a high phase down to a low phase. And so it's that cutoff frequency in those cases. The gain for the Web Audio API's implementation is that the boost or cut is given in decibels. That's often done, but not always by others. And note that a lot of the filter types don't have a gain. So low pass one, you're not trying to boost or cut anything, so there's no need for a gain parameter. The Q value, keep in mind that the low pass and high pass are resonant low pass and high pass filters. So they do have this peakiness right before the transition. That's defined by the Q. A large value of the quality factor makes the response more peaked at the cutoff. But for bandpass, peaking, and notch filters, the Q is really defining how wide that bandwidth is that you keep or remove, boost, or cut. Okay, let's look at an example. So here I have two routines, two files, an HTML file and a JavaScript file. And what I'm going to be showing you is a bit of code for listening to and playing around with the built-in Biquad filters and trying to get an idea of how they work and what they do. So we're going to have a start button, which we call make noise. We will generate some noise and listen to what happens with that noise when the noise is passed through a filter. But we're also going to view the filter's magnitude response. So we have a canvas, and here I'm using some JavaScript API that's outside of the Web Audio API. It's intended really just for graphing. Then we have a selector, which is sort of options in HTML, where we use that to specify the filter type we're working with. And we have sliders for frequency, Q, and gain. What are we going to do with all this? Well, we define two contexts here. We have one context for the audio and a different context which we use for the canvas, because canvas also one defines a context for graphing. And we will plot our magnitudes, which we get from analyzing the frequency content in the signal. So don't worry too much about that now. It's all just so that we can show what's happening with our Biquad filter. We define a Biquad filter where it defaults to having a frequency of 1000, a Q of 1, and a gain of 1. And I believe the type of the filter also defaults to a low pass filter, but we didn't say that. Then we say if anything is called back, so we run this UI, which stands for user interface callback function, if the selector is used, or if any of these range controls for frequency, Q, and gain are used, in which case we update all of those values. I did this just so I don't create many different functions. It's a tiny bit slower, but much shorter code. And then we get the frequency response. Now that's a method associated with a filter. Any filter's parameters, I can then get what the magnitudes are and the phases are for different frequencies. So the information I need to do the plots, like what I just showed in the slides. So this method is associated with the filters get frequency response, where I need to pass that arrays for frequencies, magnitudes, and phases. And it then gives a set of frequencies and the resultant magnitudes and the resultant phases for each of them. The next few lines are just to plot those values, where I clear a canvas and I begin plotting. I do lines of essentially plotting what the magnitudes are at the different frequency values. And here I'm creating noise, but I'm not using an audio worklet to do it. I simply have a buffer. Let me see if I can make this slightly bigger for you. A buffer for creating 1 second of noise. I fill that buffer. So first I define a buffer, 1 channel, 1 second at a given sample rate. So the sample rate number of samples over 1 second of samples, and I fill that buffer with random numbers, and that buffer is going to play out continually. I simply then connect the source, which is that noise buffer, to the filter and connect the filter to the output destination. And I make sure, because this is a buffer source node, it's a source node, it needs to be started. Okay, let's find out what this did. So here's the canvas, not really showing anything yet. And I have this button for make noise. I have a selector with all the different types of filters. Let me just see if I can increase the size a bit. Hope it works. Yeah, that's good. And here. So it sounds a bit like an annoying whistle, but the frequency of that whistle, or the pitch, is what's associated with the single sine wave. It's just a lot of noise around that frequency as well. And let's try working with one of them that uses all 3 parameters. So the graphing tool is very simple, but you see what sort of relationship between the input and the audio frequency, what happens to your